Hey everybody, it's Mr. Roy. We're doing a review here of our linear systems of equations for our exam. So we're going to jump in on lots of different ways of solving systems of linear equations, looking for that solution, which of course when we do it graphically is our point of intersection, and that's actually where we're going to start. We've got two equations here, and we're going to start by graphing them in order to try and find our solution, our point of intersection. Now these two lines are two very different looking ones. One of them is in our y equals mx plus b form. So there's our slope right there, and there's our y-intercept right there. So that's actually going to make it nice and easy for us to graph. Let's graph this one. Here we go. Our first one is a y-intercept of 1. So let's put in our y-intercept of 1. Now our slope is going to tell us where to go from there. This is our rise, and this is our run. Now we know our rise means how far we go up, but that's a negative number. So we're actually going to go down 1. Our rise is going to be down, and our run is over 2. So down 1 over 2, point right there. Down 1 over 2, point right there. We can also go the opposite direction. So over 2, up 1, over 2, up 1, over 2, up 1. Okay, so there's our nice line. I'm actually going to draw a line through this so we can see it nice and clearly, and that should give us our point of intersection when we get our other line on there. Okay. All right, there's my very nice line. Let's do the other one now. The other one is going to be easier to graph using intercepts, x and y intercepts. So to find my x-intercept, I'm going to set y equal to 0. So I'm going to say 2x minus 0, so we won't write that because we're setting y equal to 0, equals 4. So divide both sides by 2, we end up with x equals 2. So that's my x-intercept. That's going to be right here. Lo and behold, we actually already found our point of intersection. But let's do our y-intercept while we're at it, hey? Just so we do the whole thing here. So our y-intercept, how do we do a y-intercept? We're going to set x equal to 0. So that would be 2 times 0 is 0. So we're left with negative y equals 4. So that means y equals negative 4. So that's 1, 2, 3, 4 down here. Okay, so let's actually draw that line on. So our line is going to look like that. So we used intercepts to draw this one. So when it's in standard form, intercepts are going to be easier. You set the y equal to 0 to find the x-intercept. You set the x equal to 0 to find the y-intercept. There's your line. If it's in y equals mx plus b form, we draw our y-intercept, and then we follow our slope to see what our line is next. Okay, so how did we actually solve this? We did. So we say, therefore, POI for point of intersection is going to be equal to 2, 0. That's the point on our graph where those two intersect. Okay, so that's graphing. Okay, next we got number 2. Determine if this point 3, negative 4 is the solution to this system of linear equations. Now we know how to solve linear equations. We could do one of our methods of solving it, but we just want to know if this particular point is going to be the one. So here's what I got to do. I got to try this point in both equations. And if it does work in both equations, that means it's a point on both equations, then that must be the point of intersection. Because if I have some lines like that, if the point is on both of those lines and they're not the same line, they're not on top of one another, then that has to be the point of intersection. So let's see if this point works with both of them. Okay, so I'm going to put a little star here and I'll say try the point xy in both equations. Probably be useful here if I labeled my equations, right? So let's call this equation 1 and equation 2. And so we're going to say sub into equation 1. Let's give that a try. So we'll go 2 times x. X in this case, we're going to try the 0.3 minus y. Y in this case is going to be negative 4 equals 10. So let's see if that works out. If left side equals right side, then we know that is indeed a point on the line. So let's see if that's the case. 2 times 3 is 6, minus negative 4 is actually plus 4. So 6 plus 4 is 10, so 10 equals 10, that means yes, check mark. That point is on the line. Now let's try equation 2. So we'll go sub into equation 2. Let's try that in a different color so we don't get it mixed up. Well, what's our x value? Our x value is 3, so we'll put a 3 in where that x is, and then we have 3 times y. Y is negative 4. Does that all equal 9? Let's find out. So 3 plus, whoopsie. It's going to be 3 minus, because 3 times negative 4 is negative 12. So 3 minus 12 equals 9. Is that true? 3 minus 12 is actually negative 9. So that is not true. So I'll go, 9 does not equal negative 9. No good. So then we'll say, therefore, this is not the solution. There's another solution. You could plug those into Desmos and find it pretty quick and easy, or use one of our other methods of solving. I want to point out a bit of language though. We would not say that 3, negative 4 is the solution to equation 1. We could say it is a solution to equation 1, because equation 1 is a line, right? So you could have infinite points on that line going either direction. So we could say it is a solution to equation 1, but it is not the solution to the system of linear equations, right? For a system of linear equations, you can have 0, 1, or infinite solutions, but we only have one solution if the lines have different slopes, right, if they cross one another. So this is not the solution to the system of linear equations, because the point 3, negative 4 is not on line number 2. If we want to picture this, we can think of something like, here's 2 lines, and here's where they intersect, and here's our point. It's on one of the lines, but it's not on the other line. So there's another point that is our point of intersection, and 3, negative 4 is not it. Okay, number 3, how many solutions does this system have? Knowing how many solutions is something that's an important skill, right? We could have a couple of different things. We could have parallel lines. If we had parallel lines, well, those are not really parallel, but let's pretend they are. If we had parallel lines, we would say 0 solutions. If we had lines that were in some way had a different slope, we would say there's 1. And if we had lines, I don't want you to write this down here because I'm going to use this space. If you want to write this down somewhere else, though, that could be useful. So 0 solutions, 1 solution. What's our other possibility? Well, we got one line here and we got another line right on top of it. That would be infinite. Infinite solutions. Okay, let's clear those out of there. Those are our 3 situations. So how can we tell if it's one of those situations? Well, we gotta have a look and compare our 2 equations, right? We gotta have a look and compare our 2 equations and see. Right now they're in standard form, which can make it a little trickier to compare our 2 equations. Let's label them. Let's call this one 1. Let's call this one 2. Let's take number 1. We're going to do equation number 1, and we're going to multiply it by 2. Okay, because I notice that'll make my x values the same. Let's see what we get. So x times 2 is 2x. 3 times 2 is 6. 3y times 2 is 6y. And 4 times 2 is 8. So I thought maybe I can make them the same by multiplying it by 2. This is an equivalent expression to number 1, right? So this is still equation number 1. It's been multiplied by 2 on both sides, but it's still the same equation. It's just a equivalent form, just like 2/4 is equivalent to a half, right? But it would, when we graph it, it would look the same. Now, are these equations the same? No, they're not the same. Because although we have 2x, we have minus y in equation number 2, minus 6y, and plus 6y in equation number 1. So they are not the same. So therefore, we don't have infinite solutions. We can rule that one out. Okay, so I can say it's not that one. Let's write down what we know about that though, right? So if it's all multiples, like if all the things in equation 1 could be multiplied by something to get all the things in equation 2, if it was all multiples, if one was all multiples of the other, we would say it's infinite solutions, right? We would say infinite solutions. So if I had, for example, don't write this down, but I just want to give you an example. If I had like 5x plus 2y equals 3, I could think of a multiple of that. Let's multiply everything by 3. 15x plus 6y equals 9. That's the same line, right? This equation right here is just a multiple of this equation right here. So if it's all multiples, then it's going to be infinite solutions. It's actually the same line just graphed right on top of one another. Okay. What about another possibility? If the slope is the same, but the y-intercept is different, then we would say that they're not, that we have no solutions, right? If the slope is the same, but the y-intercept is different, that means they're parallel, like that. Again, not exactly parallel. Ugh! Let's put them in y equals mx plus b form, right? Let's put them in y equals mx plus b form. So I'm going to take my equation 1, and I'm going to change it around. So I'm going to say, okay, let's start with x plus 3y equals 4. Let's subtract x from both sides. So we get 3y equals negative x plus 4. Now let's divide all sides by 3. So we get y equals negative a third x plus 4 over 3. Okay. Now let's do this to equation 2. Let's put it in y equals mx plus b form. So we got 2x minus 6y equals 8. Let's move the x over. So we got negative 6y equals negative 2x plus 8. Let's divide both sides by 6, by negative 6 rather. We end up with y equals negative 2 over negative 6x plus 8 over negative 6. Let's clean that up a bit. Negative 2 divided by negative 6, we could write that more simply as positive a third, because a negative divided by a negative is positive. And 8 divided by 6, we can simplify that a little bit. It's going to be a negative number. So I can subtract, and we can simplify that to be 4/3. Okay, so question is, are these the same? The answer is no, they're not. Their slopes are different. They might look the same, but the signs are different, meaning one is going up, the other's going down. So their slopes are different, therefore they have to intersect somewhere. They have to intersect somewhere. So I'll say slopes are different. If the slopes are different, that means one solution. Because they have to intersect somewhere if their slopes are different. So we'd say this does have one solution. That's the answer. That's the answer. There is one solution because their slopes are different. We may have a situation, though, where they are parallel to one another. In that case, their slopes would turn out the same, but our y-intercepts would be different. So we can say, okay, slopes same, but y-intercept different, that's going to be 0 solutions because there will be parallel lines that never touch. They got the same slope, so they keep going on forever, but they're offset a little bit. So that would mean 0 possible solutions. So in this case, we have different slopes. That's all we need to know. One solution. One solution because slopes are different. Now, you might be able to tell that the slopes are different just by looking at one another. If you can look at it and say the x and y values aren't multiples of one another in terms of comparing the two lines, you wouldn't necessarily have to put them in y equals mx plus b form, but it is a lot easier to see it when it's in y equals mx plus b form. A lot easier to see. Okay, let's go on to number 4. Solve by the most appropriate method. We got 3 of these. There's 2 of them I'm going to solve kind of the same way with substitution, and a third one that I'll sub with elimination. So I would pause the video here, see if you can do this, because this will really test your skills, right? If you can do all 3 of these, no problem, then you know, okay, I'm fine with this stuff. I'm ready for the exam. If you find you're having trouble with substitution, that's when to practice. If you find you're having trouble with elimination, that's when to practice. If you're having trouble with both, then you know, okay, solving systems of equations algebraically is something that I need some help with. Okay, need some more practice. Okay, so we're going to do for our first one substitution, but there's a special kind of substitution that's called comparison. That's when we have the same variable isolated for both of them, right? So basically what we can do is we can just compare the two equations because they're both equal to y. If they're both equal to y, that means the stuff on the right must be equal to one another. Another way of thinking about this is you can just say, I'm going to take the, actually let's not do that. Let's use my actual dotted line here because I have one. I can take this, that's nicer, isn't it? And I can substitute that in for y because I know it's also equal to y. So this is substitution, but this specific type where they're both equal to y is often called comparison because really you're just comparing one side to the other. So this side is equal to y and this side is also equal to y, so I can write them like that. Now it's just a matter of solving my equation. I got to get the x's over to one side, so let's subtract 2x from both sides. 3x minus 2x is 1x. I could just write that as x. What do I do next to get x by itself? Let's add 4 to both sides to get rid of that 4. So we end up with x equals 7 plus 4 is 11. Okay, so there's my x value. I'm halfway done. Now I need to figure out my y value. Well, I got 2 equations that could do that for me. I can pick whichever one I want. I think my second equation would make it easier such that I don't make a mistake. So I'll go 2 times 11 plus 7. That's going to be 29. Now, it's really good to actually label your point of intersection and say 11 and 29 because that shows you really understand what you're doing. Okay, so that's my point of intersection. Let's try my next one here. Sorry, I'll leave that for a minute. What am I doing? You can pause your video if you want to write it down. You can just pause your video. Okay, here we go. This next one, kind of similar, but I have x isolated here, but I don't have the other x isolated here. But that's okay. As long as I have one of the variables isolated, that's actually pretty easy to work with. This is substitution. So I'm going to take what x equals, because I have it isolated, and substitute it into my other one. So this is called substitution. You might be wondering, do you need to memorize these terms? No, except I might ask you to solve something by substitution. I might say on the exam, solve the system of equations by substitution, or solve the system of equations by elimination. You have to be able to remember which is which such that you can do the thing, but I wouldn't ask you like a definitional question or anything like that. Okay, so we say, all right, let's substitute our x into there. So here we go. We'll go 3, and where x was, we're going to put 2y minus 5 in its place. And then we'll write everything else out the same. So again, my hint that I was going to do that is right here. I had one of my variables isolated. That should tell me right away. Substitution is the way I want to go. Okay, let's multiply through the brackets here. So 3 times 2y is going to be 6y. 3 times negative 5 is negative 15. Before I do anything else, I can collect my like terms. So this is going to end up being 6y minus 1y, that's 5y, minus 15 equals negative 10. Let's add 15 to both sides to get rid of that minus 15. So I got 5y equals negative 10 plus 15 is going to be 5. Divide both sides by 5, I'm going to get y equals 1. So I'm halfway there. Now, which equation do I substitute into? Well, no, the first one, number 1 here, is much easier to substitute into because x is already isolated. So let's do that. So x equals 2 times whatever y is. We know it's 1 now at the point of intersection. Minus 5. So 2 times 1 is 2, minus 5 is negative 3. So we say, okay, my point of intersection is negative 3 for my x value, 1 for my y value. Okay, I'm going to create a new page here and then do my next one. Okay, so this appears just next to the other two. These are two equations in standard form, meaning I've got my x and my y terms over here on one side, my regular number on the other side. Okay, so let's do elimination. This is going to be elimination. So when I do elimination, that reminds me I need to add or subtract equations. Whichever is going to get rid of one of the variables, right? Whichever is going to get rid of one of the variables. Now I may have to first multiply one of the equations by something. I would multiply everything on both sides to make them equal to one another. But we're lucky. We don't actually have to do that because in this one, we've got a 3 here and a negative 3 here. That means if we add these equations together, the y's will cancel out. We don't have to multiply any of the equations first in order to make that happen. So let's add our equations. We're adding them because that will make the y's disappear. If I subtracted them, I would have 3y minus negative 3y, which would be like adding. We'd end up with 6y, which we don't want. So let's add them together. 2x plus 1x is 3x. 3y plus negative 3y is 0. And 4 plus 2 is 6. So that means we have 3x equals 6. Divide both sides by 3. X is 2. Let's sub it into our equation. I think I want to use the top one. First one, that looks easier. So I'll go 2 times 2. Everywhere I see an x, I'm going to put in a 2. Plus 3y equals 4. 2 times 2 is 4. Now let's subtract 4 from both sides so I can get the y by itself. You might say, hold on a minute, Mr. Roy, hold on a minute. 4 minus 4 is 0, so 3y equals 0. So what's y? Well, let's divide both sides by 3. to get a y there. 0 divided by 3 is still just 0. So y is 0. If y is 0, 3 times y is also 0. Okay, so my point of intersection is going to be x value of 2, y value of 0. Okay, so that was a pretty straightforward one. You're going to want to practice some of these on our review that are ones where you're going to have to multiply one of the equations in order to make those coefficients the same. Or the same but an opposite sign. So you can add or subtract the equations and get rid of the y's or get rid of the x's. Okay, we're rolling along. Just a little more, and then we're going to jump into some of these word problems now. I want to try 2 of our word problems. I want to try one that is one where it's like a money one, and I want to try one that is a rate one, like a speed traveling type of one. Okay, so here's our one. So I'd pause the video here, see if you can write your equations, and then see what you think about solving them from there. Okay, you're back. Let's try this out. A coin box of a vending machine contains $6.20 in dimes and quarters. Dimes and quarters. There are 32 coins in all. How much of each kind are there? Okay, so important information. Let's pick it out. The amount of money is $6.20. And that's in dimes and quarters. Now, dimes and quarters are worth different amounts. So when we make an equation that's going to be equal to the dollar amount, 620, we're going to be multiplying one of our variables by what a dime is worth and multiplying the other one by what a quarter is worth. So let's actually write that one right now. Here's my first, no, I got to do my let statement then. So let's hold on just a minute. My other important piece of information, there are 32 coins total. So in a situation like this, my variable should be the actual physical things, right? And then when I want to know how much they're worth, I multiply them by the value of that thing. So anytime we got a money problem, we inevitably end up saying let x equal the number of dimes. So that's not how much they're worth, that's the number of actual physical dimes that there are. And that y equal number of quarters. Let's write that first equation. We know it's going to be $6.20. That's what it's going to work out to. Well, what are we going to do with our x and our y? Well, our x is worth 10 cents. So I'll go 0.1 times x. That's how much money I have in dimes. And my quarters are worth 0.25 times y. That's how much money I have in quarters. So my money in dimes plus my money in quarters is $6.20. My other equation is just going to be the number of coins. Dimes and quarters, there's 32 in total. So those are my 2 equations. Now to solve this, you'll notice this is set up in standard form. That probably means that elimination is an easier or at least a faster way of doing it. If you like substitution, you could get y by itself by going, okay, y equals 32 minus x, and you could take that and you could sub that in for y here. That's going to be a bit messy, so I'd rather not do that. I'm actually going to do elimination because it's a bit more neat. So I'm going to call this number 1, and I'm going to call this number 2. And I'm going to set it up over here, and I'm going to say, here's number 1. I'm going to say number 1 times 0.1. That's going to change my x to be 0.1x, and that means I can eliminate my x's. So let's do that. So I'm going to take my equation number 2. I'm going to say, I mislabeled it. I'm going to say equation number 2 times 0.1. So what am I going to end up with? I'm going to end up with 0.1x and 0.1y equals, what's 32 times 0.1? That's easy, it's just 3.2. Okay, now what's my other equation? Equation 1 was 0.1x plus 0.25y equals 620. We can just write that as 6.2. Okay, now what am I going to do with these? If I add them together, none of my variables will go away. So let's subtract them. If I subtract them, the x's are going to go away. 0.1x minus 0.1x, that's 0. So that's why we did all that. That's what we wanted. 0.1y minus 0.25y. Well, I got to get rid of that plus I just wrote because it's actually going to be minus 0.15y. And what's 3.2 minus 6.2? It's negative 3. Let's divide both sides by negative 0.15. Divide both sides by negative 0.15. What do we get? We get 20. So y is 20. So what's our x going to be? Well, that's pretty easy, right? We know x plus y equals 32. So we'll say x plus 20 equals 32. So that means x equals 12. So we don't have to write it as a point of intersection in this one because this is like got some real context. So let's just do a therefore statement with context. Therefore, there are 12 dimes and 20 quarters. Okay, so tricky, but these coin questions, value questions, are always going to turn out the same. They're always the same method, just the numbers change. So if we can get really used to that method, we can be really prepared for a question like that. Here's another kind of question that we saw very often in this unit. This is a very frequent one. It took the high school volleyball team 5 hours to travel to a tournament. They traveled by bus and plane a total of 1,320 kilometers. If the bus averaged 40 kilometers per hour and the plane averaged 600 kilometers per hour, determine the time they spent traveling by plane. Okay, it's really important that we remember, first of all, distance has two parts to it. How fast you're going and how long you're traveling that at that speed. So how fast we're going and how long we go for. Let's do a little table here. Get myself some lines. So we'll put one there, put one there, put one there. So this is a little grid box. And we use the same sort of one for all of our questions of this type. Okay, so we said, okay, we've got distance, speed, and time. Right? Those are the three things, distance, speed, and time. And we've got a bus trip, and we've got a plane trip, and we've got a total. So this little table will get set up the exact same way every time. So that's one thing we should get used to. Now, we don't have to do a let statement because we're going to have it involved in our table. So for this particular one, it's okay if you don't do a let statement. I'll be able to see what's what. For these ones, though, we always have our x and our y values as our time. And our total time is 5 hours. So we can always put those in that column, our x and our y value. What's our speed? Well, first we're going 40 on the bus and we're going 600 on the plane. We don't have a total for speed because that doesn't make sense for average speed. Now what's our distance? Well, it's right over here, right? Don't forget about that. So our distance is speed times time. Speed times time. And what's our total distance? It's 1320. So now I got my two equations, right? I got my equation right here, and I got my equation right here. So let's write our two equations. First one, nice and easy. It's x plus y equals 5. That's our time equation. What's our distance equation? 40x plus 600y equals 1320. So there's my two equations. These are in standard form, so solving them through elimination is going to be easier. I'm going to rewrite my equation number 2. Now, how can I change equation number 1 in order to be able to cancel some stuff out? Well, I could multiply by 40. I'd have to do it to everything on both sides. So I would now have 40x, and I would have 40y, and 5 times 40 would be 200. Which I know 5 times 4 is 20, times 10 would be 200. Now what do we do with this? Well, if we add them together, we won't get rid of any of our variables, so we have to subtract them. 40x minus 40x, that's 0. 40y minus 600y, negative 560y. And 200 minus 1320 is negative 1120. Now before we go any further, you might have said, hey Mr. Roy, what if I multiplied them by negative 40 and then added them together? Would that work? Yep, that would work great. You might say, what if I multiplied them by 600 and then subtracted to get rid of the y's? Would that work? Yep, that would also work great. So your solution may look a little different than that depending on what tactic you want to take. Do you want to eliminate the x's? Do you want to eliminate the y's? What do you want to do? You could also use substitution, right? Take equation number 1, rearrange it, y equals 5 minus x, and plug that in and work it out. But that is going to be more work. Let's divide both sides by negative 560. So we'll get y equals 2. Well, that was a nice even answer. You would think someone planned it out that way. Okay, so y equals 2. Let's find out what x equals. X plus 2 equals 5. This is going to be the easiest math you do all year. Subtract 2 from both sides. X is 3. Let's do a little therefore statement. We'll say therefore they spent, y is our plane. So 3 hours on the bus and 2 hours on the plane. Now that I look at it, I bet it's just asking for once. Yeah, determine the time they spent traveling by plane. So I only needed my y value. I was actually done. I didn't have to sub in for x, but hey, what the heck? I'm doing some extra work today. Okay, that's it. That's our review of systems of linear equations. I'd like you to take a moment now and just reflect on which stuff in this review did you find easy and straightforward? Which stuff did you find moderately challenging? Which stuff did you find really difficult? Identify the things where you feel like you need the most practice. Is it solving by substitution? Is it solving by elimination? Is it solving by graphing? Is it word problems? Right? Where do you need the most practice? And that's where we're going to focus our efforts first.